Today you are going to learn how to use matrices to represent linear transformations in 2 dimensions and in 3 dimensions. A transformation matrix M transforms the point 32 to 73 and minus 21 to 05. In order for us to work out this matrix M, we have to set up this equation. So we have the matrix M being represented by A, B, C, D. So these are unknowns that we're going to find. 3, 2 is the input, and 7, 3 is the transformed coordinate. If we multiply this out, this would give us 3a plus 2b equal to 7 and 3c plus 2d equal to 3. We can do the same thing for the second set of coordinates, resulting in 2 more equations. We can then solve these simultaneously. If we take the first one here and the first one here, we can solve these to work out the values of A and the values of B. And then if we take the other 2 equations, so this one and this one, we can solve those to work out the values of C and D, which means M has a value of 1, 2, minus 1, 3. A rotation of 90 degrees clockwise, followed by another rotation of 90 degrees clockwise, is the same as a single rotation of 180 degrees. Now we can show this using matrices. Here are the transformation matrices that represent rotations 90 degrees clockwise. If we multiply these two together, we get minus 1, 0, 0, minus 1, which is a rotation of 180 degrees. So what we can do here is show that if we apply multiple transformations, then we can use matrix multiplication to work out what the single transformation would have been. Now we can demonstrate this idea further with these 2 transformations. So we have matrix A representing a stretch along the x-axis by a scale factor of 2, and matrix B representing a reflection in the line y equals x. We're going to complete a method similar to how we did in a previous lesson, where we draw the rectangle with the coordinates 0, 0, 2, 0, 0, 1 and 2, 1, and then draw the image of the rectangle under the transformation A, followed by the transformation B. And then we're going to calculate the single transformation that represents A followed by B. And then we're going to check to see if our original coordinates are indeed correct. And finally, we will repeat this for the transformation B followed by A. Okay, so taking a look at those coordinates then, so we have A, B, C and D, and we're going to perform the first transformation A, which is a stretch along the x-axis by a scale factor of 2. So this will take our coordinates from 2 up to 4 here for B, so this will be B prime. And C, if you remember, we'll go to C prime up here. A will remain the same and D will remain the same. Then if we use the second transformation, matrix B represents a reflection in the line y equals x. So let's just draw that on now. So the line y equals x is here. Just extend this a little bit further below as well. Okay, so I'll deal with A first. As A is on the line of reflection, it will not move. So A will become A double prime. Then if we deal with B, now B is over here and it has coordinates of 4, 0. And so in the line y equals x, it will be mapped up here to the coordinates 0, 4. So this is B double prime. C, which has coordinates 4, 1, reflected in y equals x, we'll go to this position here, which is C double prime, and that will have coordinates 1, 4. And then D will go from its position on the y-axis to this position here on the x-axis, and this is D double prime. So if we draw this, if we sketch this in, under both of those transformations, A followed by B, we have this rectangle. Now let's take a look at the matrices that represent the transformation A and the transformation B. So A is a stretch along the x-axis by a scale factor of 2, which we found out last lesson was 2001, and B can be represented by 0110, so that's the reflection in the line y equals x. Now if we think about this process, how did we work out, how would we have transformed each of those original coordinates? If we applied matrix A first, we would have had to have done 2001 multiplied by each of the coordinates. So let's, for example, take C. So C has coordinates of 2, 1. We transformed that coordinate under the transformation of A. Now on our diagram, we can already see that this coordinate is 4, 1 over here as C prime. But let's just double check as we go through. So that would be 2, and indeed it is 2, excuse me, 2 times 2 is 4, and the last one there is 1. So from here, this coordinate represents C prime, and we would then have to apply the matrix B to this coordinate 4, 1. So we would then apply 0, 1, 1, 0 to C prime 4, 1, which would give us 1, 4. Which if we look up here at the top, this is what we've got for our C double prime. Now, the order in which we have performed these transformations is important. We applied transformation A first, followed by transformation B. Now we can write this, if I just get rid of my annotations at this point, we could write this as B A. So 0, 1, 1, 0, 2, 0, 0, 1. And if we multiply these two together, this should give us the single matrix that represents both of those transformations taking place. A followed by B. So multiplying, this gives us 0 and 1 and 2 and 0. And we can use this matrix with that original point C to check whether this works. So 0, 1, 2, 0, does it take C to C double prime? So 2, 1, which is our C value. And if we multiply this out, we get 1, and 2 times 2 is 4. And yes, indeed, there is our C double prime. And so this matrix represents the transformation of A followed by B. This time we're going to apply transformation B followed by A. So I'm going to do this on the diagram first of all. So we have A, B, C and D. And if we look at the first transformation then, so B, this is, we need to do the reflection. So if I pop the line of reflection y equals x on this diagram, and then reflect each of those vertices in this line. So A will be mapped to itself, so we'll call that A prime. B is 2 across there, so this will be mapped to this point on the y-axis, that's B prime. And C will be mapped here to C prime, and D will be mapped to this point here, which I'll just put down there as D prime. And then let's transform this again using matrix A. So this time it's going to represent a stretch along the x-axis by a scale factor of 2. So a different pen. Now A prime and B prime will remain the same here. I'm writing B again, excuse me. So this is A double prime, and B prime is the same as B double prime. They don't move, they are not transformed. And so as we are stretching along the x-axis, we are moving C prime and D prime by a scale factor of 2. They currently have a length of 1, and therefore their new position, D prime, will be mapped to where B originally was. So this is D double prime, and C prime will be mapped to this position here as C double prime. So our new shape, if I draw a sketch of this, so this is the image of that original rectangle, which is now a square. So let's see what this would look like if we were to use the matrices instead. Now, from that previous slide, so we had A represented by 2, 0, 0, 1, and B by 0, 1, 1, 0. And as we said last time, B is applied first, then A. So we are working out A, B, because it would be this combination that would then be multiplied by the coordinates. And we can check this as well. So we have 2, 0, 0, 1, 0, 1, 1, 0. Let's multiply these two together. So we have 0, 0, 2, and 0, 1, and 0 there. So this is the transformation matrix that represents B followed by A. So let's check this. If we use the same point again, let's use C. So if I just get rid of those extra bits there, just above, give me a little bit of space. So 0, 2, 1, 0. Let's see what we are expecting. So we're expecting C double prime to have the coordinates 2, 2. And C had coordinates of 2, 1. Multiply these together. So we have 0 times 2, 2 times 1, that is 2. 1 times 2, 0 times 1, that is 2. That works. And we can check any of these. So we could check A, B, C or D, and they would all work with this. Or indeed we could check by multiplying individually with matrix B followed by matrix A. So it is this matrix here that represents transformation by matrix B followed by matrix A. Successive transformations. If you had two transformation matrices A and B and you performed successive transformations starting with A followed by B, you would calculate the single transformation matrix using BA. But you need to read it this way around. A comes first, B comes second. This means A, then B. Now we're going to take a look at some 3x3 matrices that represent transformations. So what is the matrix M? That represents a reflection in the plane x equals 0. Now x equals 0 is sometimes referred to as the YZ plane. And you can see here, if you imagine a piece of paper that lies across Y and Z, and x is poking out at 90 degrees to both the y-axis and the z-axis there. Now let's take a look at what would happen to I. I at this point is a column vector 1, 0, 0, and as it's reflected in the plane x equals 0, it will have a position of minus I. So this transformation matrix becomes minus 1, 0, 0 for the first column. That's how I is mapped under this transformation. Now the other point, so we need to take a look at J. And J would be 1 up on the y-axis. So where would this be transformed to? If J is lying on that plane x equals 0, then there is no reflection, it doesn't move. So it does not change its position. And so the column vector that represents this is 0, 1, 0. Notice how as you extend it from 2 dimensions into 3, that you gain that extra 0 there at the bottom for those two. And then we just need a final position for the z-axis here. So this would be represented by k, so I, j, then k. And k would be 0, 0, 1. Notice how this is also on the plane x equals 0 and therefore remains unchanged under the transformation, and therefore is mapped to 0, 0, 1. And so the matrix that represents a reflection in the plane x equals 0 is given by this matrix here, matrix M. So for your notebook, a reflection in the plane x equals 0 is represented by matrix M. In the plane y equals 0, similarly, notice the differing change there with where the position of the minus 1 would be. And then for a reflection in the plane z equals 0, we change that 1 in the final column to minus 1. Let's take a look at the matrix M that represents a rotation of 90 degrees about the x-axis. So a rotation means that the x-axis will be fixed and it's y and z that would be rotating around. So let's take a look at what would happen to I in this situation. So as I is on the x-axis and the rotation is about the x-axis, I hope you can visualize what's going on here. So imagine you are rotating around like this. Then in this case, I would remain unchanged. So 1, 0, 0 becomes 1, 0, 0. Let's take a look at J, which is positioned on the y-axis. So as this rotates round 90 degrees, now as you visualize this, each of these axes are at 90 degrees to each other. So as this rotates round, it moves into the position of where K would have been. Now J has the position of 0, 1, 0, and if it's moving to the K position, it moves to 0, 0, 1. Let's take a look at that final point then. So K, which is on the z-axis, as this rotates round, so we are now moving down here, I'm going to move underneath, and this is in the position minus J, and this represents 0, minus 1, 0. Now you don't need to learn these rotation matrices for the 3x3 transformations here, as they are all in the formula book, but just notice the difference in the position of where the 1 is, so the 1, 0, 0 in that first column to where it appears in the second column when you are looking at a rotation about the y-axis, and the third column for a rotation about the z-axis. And then just those positions of the sine theta and cos theta and the actual signs of those. And that bit represents the angle transformation, similar to the 2x2 matrix for rotations of an angle of theta. Please turn to page 186 and complete exercise 8D.